In the previous lesson, we took a look at two number systems, binary and decimal, which are actively used in digital electronics. In this lesson, we'll move forward and apply the on-off true-false quality that the binary number system offers us and see how it applies to logic gates and Boolean algebra. Boolean algebra uses three operators to perform mathematical Boolean operations. They are AND, OR, NOT. Logic gates are a graphical way to represent Boolean algebra equations through logic diagrams. And with a logic diagram drawn, you can move to digital hardware and actually build the circuit. The first Boolean expression and logic gate that we'll look at is called the AND gate. Graphically, it looks like this symbol, and algebraically, it is represented by this dot. But like multiplication, you can actually just have the two input symbols x and y together, and it means that they should be ANDed together. The way that this logic gate works is with binary inputs. The inputs and outputs are defined by what is called a truth table. As you can see on your screen now, this truth table shows that only when both inputs are logic 1 can an output from the logic gate of logic 1 be achieved. If either of the inputs is a logic 0, the AND gate's output is also a logic 0. The next Boolean operator and logic gate that we'll look at is called the OR gate. Graphically, it looks like this, a more curved version of the AND gate. The Boolean algebra representation of OR is a plus sign. Just as with the AND gate, an OR logic gate has a truth table that defines its function. Here, the truth table shows us that when either input signal is a logic 1, the output is a logic 1. Only when both inputs are logic 0 does the output become logic 0. The next Boolean operator and logic gate is called the NOT gate, and in Boolean algebra, it is represented by putting a line over the input like this. The NOT gate is the most simple of all the logic gates because all it does is invert the input signal from logic 1 to logic 0 or from logic 0 to logic 1. So the truth table for it looks like this. The final Boolean expression and logic gate that we'll look at is called the XOR gate, and its Boolean algebra symbol looks like this. The XOR gate, short for exclusive OR, is a special gate that combines both the OR gate and AND gates together. Here's the truth table for how the XOR reacts to different inputs. When the inputs are both 0, 0 or 1, 1, the output is logic 0. However, if either input is a 1, the output is a logic 1. This might seem like an odd operation to have, but the more tools we have in our digital logic toolbox for solving problems, the better. These logic gates form the basis of digital electronics. If you delve deeper into logic gate theory, you can discover other types of logic gates do exist, but they are all some combination of the AND, OR, NOT logic gates that we just learned about. Now that we've established the theory, let's get some integrated circuits out and see this stuff in action. For the experimentation part of this lesson, we'll go through each of the three basic logic gates, AND, OR, NOT, and verify that they work like we would expect by building a circuit and checking the truth table. First, let's check the AND gate. The 74HC08 IC is a quad AND gate device. This circle can be found on any integrated circuit chip. It tells you that pin 1 is right next to it. From that point, you can count out the identification of each pin as you see on your screen. For the logic ICs we'll be using, pin 7 is always ground, and pin 14 is always plus 5 volt VCC. The 74HC08 IC has 4 AND gates inside of it, with each of the inputs and outputs connecting to different pins on the IC. We'll only need one AND gate for this experiment, so we'll only be using pins 1, 2, and 3. Here's the schematic of the circuit. We'll build this circuit to test out the AND gate, and if you look closely, you can see the inputs to that AND gate are pins 1 and 2, and the output is pin 3. The parts used in this experiment are jumper wire from the wire kit and a breadboard. From the components kit, we'll need a 9-volt battery connector, a 7805 plus 5-volt regulator, 3 red LEDs, a 9-volt battery, a 74HC08 integrated circuit, and 3 100-ohm resistors. So let's set up our experiment. We're going to want to run everything off of plus 5-volt power, so we'll use a 7805 voltage regulator at the top of the breadboard. Here, pin 1 connects to the plus 9-volt connector's input, the red wire. Pin 2 connects to the plus 9-volt connector's ground, the black wire. And pin 3 is the plus 5-volt output from the 7805. We'll connect the 7805's pin 3 to the power bus line with a yellow wire, and pin 2 to the ground bus line with a green wire. 2 red wires connect the plus 5-volt power and ground to a second bus line on the breadboard. The 74HC08 AND gate IC will be placed in the middle. Notice that it fits perfectly. Breadboards are designed to be used specifically with these type of PDIP integrated circuits. Connect plus 5-volt power to pin 14 and ground to pin 7. And now we're ready to test the AND gate. To confirm the truth table, we'll need to give the AND gate 2 input signals and view the output. As per the schematic, we'll connect 3 100-ohm resistors to the AND gate at pins 1, 2, and 3. And then connect each of those resistors to an LED that goes to ground. These 3 LEDs will represent the 2 inputs to the AND gate and the 1 output from the AND gate. If an input or output to or from the AND gate is a logic 1, the LED will turn on. If it is a logic 0, the LED will be off. With the battery plugged in, the system is turned on. The 2 yellow wires will be used to change the state of the system. The first state that we're looking at right now is input of 0, 0, which yields an output of 0. Now, using the 2 yellow wires, we'll change input states between logic 0 and logic 1 to verify the truth table. When input is 0, 1, output is 0. When input is 1, 0, output is 0. And when input is 1, 1, output is 1. And that is how the AND logic gate works. Let's perform the same experiment with the OR gate. Like the previous IC, this 74HC32 IC has 4 dual input OR gates inside of it. Here's the schematic that we will be building. The only difference is that we're using a 74HC32 OR gate integrated circuit. That means you can actually just remove the IC from the previous experiment and put the 74HC32 in exactly the same spot. Now let's go through the truth table again and verify the OR gate does what we theoretically expect. When the input is 0, 0, represented by the LEDs on the left side, the output is 0. When we change the input to 0, 1, the output is logic 1. Changing the input to 1, 0, the output is still logic 1. And finally, we test when the input is 1, 1, and you can see the output is also a logic 1, represented by the LED being on. Thus, the OR gate follows the theory exactly. The last device that we will experiment with is the NOT gate, the 74HC04. Inside of this IC, there are 6 NOT modules that we can use. If you remember from the theory section, the NOT gate is an inverter. Whatever is input, the opposite is output. Here is the schematic for this experiment. Notice that this time there are only 2 LEDs, because there is only one input and one output from a NOT gate. For this circuit, we'll place the IC in the middle of the board and add power and ground connections. Then the two 100 ohm resistors are connected to pins 1 and 2, followed by two LEDs which connect from those resistors to ground. Finally, a yellow wire is added to give input to pin 1. Now you can see the input on the left-hand side and the output on the right-hand side. When logic 0 is connected to the input of the 74HC04 at pin 1, the output at pin 2 is a logic 1. And if we change the input to a logic 1, the output changes to a logic 0. Since this 74HC04 is an inverter, it is working perfectly, and we have just verified its truth table. The components kit also includes an XOR gate, a 7486, a NAND gate, a 7400, and a NOR gate, a 7402. Take some extra time and find the truth tables for these devices, and go through and verify that they follow the truth table using the method we experimented with just now. While logic gates alone are hard to find in the real world, their true place is actually in the bigger picture called logic diagrams. A logic diagram, like these, produces a single output given multiple inputs. Just like cars at a four-way intersection with a stoplight, the sensor for each stoplight must know if a car is present or not in order to determine if it should turn to a green light. Beyond graphical logic, there exists a written style of logic called Boolean algebra, which represents the complex input and output system of digital logic and allows you to more easily play with the numbers in order to simplify them. We'll learn more about Boolean algebra in the next lesson. In a final real-world note, digital logic, the idea that things have two states, either on or off, or true or false, is also widely used in programming languages across the board. You can see ands, ors, trues, and falses in plain English, or represented by simple symbols, but they're actually performing the same simple task that a digital logic OR gate or AND gate does.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/PyroEDU.
Next time, we'll begin to study more about Boolean algebra and Karnaugh maps. This way we'll see how logic gates can be combined together to solve and simplify complex Boolean equations.